String theory is a famous, albeit complicated, theory about the fundamental nature of our universe. If true, it would imply that its composition is inherently different than we originally thought. But how did we come to believe that the true nature of our universe was so counterintuitive? In order to understand string theory, we must first understand where our simpler models of physics began to break down. According to Georgia State University's physics webpage, there are 4 fundamental forces. Gravity is the one most are familiar with and is an attractive force most often seen on large scales. The electromagnetic force is the force of interaction between all charged particles. The strong force, which works on incredibly small scales, is what keeps the protons and neutrons tightly bound in the nucleus of every atom in the universe. The weak force is the least understood of the forces, and is responsible for things such as the decay of particles, which is directly responsible for the fusion that occurs in stars.
The standard model of particle physics is a theory describing the last 3 of these forces, as well as classifying all known elementary particles. As you can see in this picture, there's quite a few particles. We're going to focus on the section known as gauge bosons, or force carriers. According to the CERN webpage, the gluon is the carrier for the strong force, the photon for the electromagnetic force, and the W and Z bosons for the weak force. The current major problem in physics is that gravity cannot be described with this definition. Gravity is instead defined by the theory of general relativity as a geometrical curvature in spacetime. This seems to imply it doesn't have a force-carrying particle and can't fit the model. However, physicists dream of a grand unified theory of everything, and therefore proposed graviton. But when they attempted to insert the graviton into the standard model, the math fell apart.
Now comes in string theory. String theory proposes that rather than the elementary particles, the matter and forces of the universe emanate from tiny, vibrating, one-dimensional strands, otherwise known as strings. Greene states that the different vibrational patterns of a fundamental string give rise to different masses and force charges. For example, we know that the faster a string vibrates, the more energy it has. From Einstein's famous equation, we can derive that the greater energy a string has, the greater the mass is. This means that we can use strings to describe the mass of each one of our 4 fundamental particles, and similar methods can be used to describe the energy, momentum, etc. Returning to the graviton, the good thing is that string theory mathematically accounts for it, which will unite all 4 of our fundamental forces. However, the math breaks down at only 4 dimensions. In order for the theory to work properly, 10 spatial dimensions are currently required. That's one of the reasons why string theory is still just a theory. It doesn't work for our universe, which we assume to be 4-dimensional.
Many variations of string theory have been proposed over the years, each attempting to address the problems that arise the further along we go. The definition of string theory that we gave is a simple example of one of the leading theories. Using these different definitions, string theory can be used to explain many hotly debated topics of physics, such as dark matter and black holes. Whether or not it accurately describes our universe, string theory is still mathematically sound, and can therefore help us explain some of these major problems in physics today.
Thanks for watching!
I'm not getting in there.
Thought you were gonna join me.
Nope. As soon as you awkwardly looking to the side, and I'm just not there. That's it. We're done.
Yay!